Hello, Math 7 students. This is Open Up Resources, Math 7, Unit 4, Lesson 13, or 7.4.13, talking about measurement error. To get started, I want to review the things that we had in our last lesson. So we start with this quick pull. The original price of a sweater is covered up by the clearance sticker. That means we don't know what it is. But the sign says clearance is 40% off, so you know that you are getting a 40% discount. The sticker is showing the new price, and the new price says it's now $15. So what was that original price of the sweater? Pause the recording, give yourself a chance to answer this question, and we'll go over it when we return. Okay, what we're seeing in this problem is we do not know the original price. So since the original price is the thing that I don't know, that is the thing that's going to get the variable. I'll use X for the original price. We do know that it's 40% off. So whatever the price is that I'm paying, it's a discount of 40%. That means I have 100% minus 40% is equal to 60%. And I know that when I paid that original price and then got that 40% discount, I ended up paying a total of $15. That's the new price, the now price. So that means I can set up my equation to be 60% of the original price, remembering that we don't calculate with those percents, so that would be the decimal 0.6. So 60% of the original price, which I do not know, is equal to the new price, which I do know, and that is $15. So since this equation has x being multiplied by 0.6, I'm going to undo that multiplication with division, keeping it balanced. Whatever I do to one side, I do to the other side. And that gives me x is equal to, all by itself, 15 divided by 0.6 is equal to $25. So there are some mistakes, and I cannot tell what those mistakes are. So I'm going to pause the recording, let students who may want to volunteer and share their mistakes share with us, and then if they're useful, I will also add them to the recording. But I'm going to pause the recording now. Okay, one of the mistakes that was shared is a really good one, and what they did is they set up the equation like this. 0.4 times x is equal to 15. So what they are seeing is they're just saying, oh, 40%, I'm going to calculate with 40%, so that's going to be 0.4, and they skip this step right here, which is a really important step. Okay, what this means when we actually calculate this is that this would be a 60% discount. Or this is an attempt to try and do this in 2 steps, but it's only a 1-step problem. So those are the challenges there. Just make sure we're not forgetting this. If we get a 40% discount, do this calculation first. 100% minus 40% is 60%. And now we are to lesson 13 on measurement error. This is the last lesson in our unit. Then we will review and test. So this is just going to kind of piece together, or I guess give us a different type of situation where we might see percents. We focused a lot on percent increases and percent decreases, like taxes and interest and profit and discounts and all of those kinds of interesting situations. But another really common place that we're going to see percents is in measurement error. So I have given you 2 rulers. I've given you a centimeter ruler and I've given you a millimeter ruler. I want you to just start with the centimeter ruler. So push that millimeter ruler aside, don't even look at it. Just find the one that's marked with centimeters. And what I want you to do is I want you to record your 3 different line segments that have also been given to you. You're going to record that to the nearest centimeter. So again, what that looks like, students in class have been given a centimeter ruler and a millimeter ruler. They're going to start with their centimeter ruler and they're going to measure each of these line segments. You're going to be measuring to the nearest centimeter. So line segment A looks like it is almost to the 7, but not quite. And even though I know it's not 7, I'm measuring to the nearest centimeter, and so I am going to put in my table 7 to the nearest centimeter. Repeat that for line segments B and C. And then once you have done that, we will repeat with line segments A, B, and C using the centimeter ruler marked with the millimeter measurements. We'll be measuring to the nearest 1/10 of a centimeter, or in other words, to the nearest millimeter. So students in class are going to finish that up and then we'll record their measurements. For you doing this in class, print that that ruler if you can. If not, estimate those measurements based on what you see here. All right, class, what did you get for line segment B to the nearest centimeter? Carter? 7. And C? Leroya? 7. All right. And now let's repeat that process with our millimeters. So again, I'm just going to do this real quick here so that students watching the video can make their own estimates. Do their own measurements here. Okay, and what did you guys get in class? Let's fill out that table. Line segment A to the nearest millimeter or 1/10 of a centimeter. What did you get? Go ahead, Trace. Yeah, 6.7 centimeters. What about line segment B to the nearest 1/10 of a centimeter? Dallin, I'm sorry, I don't even know where that came from. Gavin, I don't. Oh my goodness. I haven't had my coffee, can you tell? I'm so sorry about that, Davin. Okay, Dylan, do you have the measurements for C? 7.3, thank you so much. It's time to pause the recording and drink some coffee, I think. Okay, which one do you think is more accurate, folks? I think it's very clear to see that it's going to be this column, right? So let's just pretend that this column is 100% accurate, that there's no error here. This is the accurate column, right? When we use a less precise measurement, are we going to get as good of measurements if we have a more precise measurement tool? So that's math practice 6, first of all, attend to precision. If we can use something more precise, let's be a little bit more precise. But we want to talk about the measurement error, because that's what this lesson is all about, is the measurement error. And we're going to come back to this in just a second. We're going to move on and then we're going to come back to this. How wrong was our initial measurement? Knowing that this one is the accurate one, how wrong was this initial measurement? I'm going to write here error. Luke, how wrong was it? Yeah, it was about 3 millimeters off, or 0.3 centimeters, right? Okay, and B, how inaccurate was that one? Gideon? 0.1 centimeters in error. And C, Dylan? How much? Double check. 7.3 is the accurate measurement, and we measured 7 here. So how much difference is that? Dylan needs some coffee too, it sounds like. Yes. You haven't had your coffee either. 0.3. Okay. We're going to come back to that. So what I want to demonstrate with this, though, is that there is going to be a little bit of error, right? We had some error when we used less precise, and I ultimately want to be able to take this error and compare it to something so we can get a percent. Let's move on to measuring a soccer field. A soccer field is 120 yards long. Pause and let that sink in for a second. How big is that? 120 yards long. Okay, I'm not going to have you answer with your hands raised. I just want you to think. 120 yards long. Han measured the length of the field using a 30-foot long tape measure. He gets a measurement of 358 feet 10 inches. Have you guys had to do something like that before? Have you had to measure something like, I don't know, the room using some measuring devices that were not quite as long as they needed to be? Were they very super duper precise? Nope. So much so that I decided I wasn't even going to grade that project, right? You guys remember that? So we already know that there is going to be some error. I want you guys to put your heads together. What is the error? Notice again, we know for sure it's 120 yards long. This is what Han measured. So what is the error? And then part 2, express the error as a percentage of the actual length of the field. Let's put our heads together. Let's work on that. I'm going to give you guys a head start. Pause the recording while you guys give it a try, and then we'll talk. Ready, set, go. How long for sure is the soccer field? What is the accurate measurement of a soccer field? Luke. Ooh, I like that. Notice that this problem gives us 120 yards, right? But he didn't say 120 yards. He says, well, this isn't measured in yards. So let's convert this measurement from 120 yards to 360 feet. That's a great start. Carter? Okay. Why is that going to be necessary? Like, why even do that? Because it is necessary. That's why. Did you not catch that? Eyes on the screen. How are you going to express this? 358 feet, 10 inches. How are we going to figure out how different that is? Okay, 1 feet, 2 inches. Good. How are you going to write that down? How are you going to calculate with that? Is this the same as 1.2? Nope, it isn't, is it? So that's why going that step further and converting this from feet to inches might actually be a little bit more helpful. Yes, Grant? However, that's exactly the point. Is that very accurate? Because you still haven't said enough sixes. I can write down as many sixes as you said. That still isn't precise. Technically, is it? Nope. And so what are you going to type into your calculator and still keep that level of precision? You can't, right? And so that's why instead of trying to do this, even though this is accurate, what Grant did here is he said 1 foot and 2 out of 12, which is 1 foot and 1/6, which is this 1.16 over bar. But calculators, they can't, I mean, you can't type in that over bar. You can't type in the 6 enough times to repeat it. And it doesn't do mixed numbers very well. So yes, there are probably some ways around it, but for what we need to do for part 2, it might also be helpful to express this in inches and even to express this in inches too. Okay, so let's convert this to inches. Someone already did that. 360 feet is equal to, was Carter, how many inches? 4,320 inches. And so again, we're just taking that 360 feet, knowing that there's 12 inches in each foot. So 360 times 12 is 4,320 inches. So now I can express the amount of error as 1 foot 2 inches, 1 2/12 of a foot, 1 1/6 of a foot, 1.16 over bar of a foot, or even better, how many inches is that? 1 foot 2 inches is how many inches total? 14 inches in error, right? And I think that that is going to be better for what we need to do next. Even if you didn't catch that, when it's time to compare, we need to make sure that our units are the same. So what is the amount of error? 1 foot 2 inches, which is equal to 14 inches. Part 2 says we need to express this error. Oh, let's back up though. Why do you think Han wasn't as precise? How come you think he didn't get that 360 feet like we know he should have? What happened, Luke? Mm-hmm. Yep. Sure. That could be. Just the fact that we're moving it is an issue. Is he going to be moving it and remeasuring right exactly where he left off? And that's a good assumption too. Maybe each time he moved it to like the end of the measuring tape, even though that wasn't part of that measurement. Maybe he got a little bit off, started maybe measuring the diagonal would actually make it probably a little bit longer. So I think that that's probably a good guess. Luke, thank you for sharing. So now we know that there is an error. We know that there's 14 inches off. Express the error as a percentage. So again, this means that we are making a comparison. Whenever it's a percentage, it's a comparison. Carter? Mm-hmm. Yes, only what we want is we want the error. So instead of doing that subtraction that you mentioned in the beginning, we're just going to focus on the error. How far off was he? He was off by 14 inches. So I don't need to subtract it from the actual. I'm just taking this actual, which is that 14 inches. And I'm comparing it to what we know for sure is the accurate measurement of, would it make sense to compare it to 120 yards? So again, here's the issue, right? We have 14 inches out of 120 yards. Those are different measurements. It doesn't make sense to compare that. Even converting it to 360 feet doesn't make sense to compare that. The only thing that we can do is keep it inches to inches, and so that would be 14 inches to the actual accurate amount of 4,320, and that is the comparison that we're going to make. Type that into your calculator. It is going to give you a decimal. Let's make sense of that, what that decimal is. Hands are busy typing things into the calculators, or they're up because they already know. Let's get going, folks. 14 divided by 4, 3, 2, 0, enter, and then your hand goes up in the air. Grant? I would like the decimal, thank you. That's good. 0.0034? 324, great. So what does that actually mean? Is this a percent yet? Nope, we need to convert it to a percent. So this is going to be, I'm just going to move that decimal place over, 0.324% error. Is that a huge, major error in his measurement? Not in the grand scheme of things, but is it accurate? So with that in mind, let's go back to our warm-up. Let's find the error on each of these ones as well. We already know how far off our measurements were, right? So this was off by 0.3. What are we going to compare it to? If I wanted to know the percent error, what am I going to compare that to? Talk with your groups. Just like here, right? I found the error, which was 14 inches, and I compared it to this. So we already found our error. What are we going to compare that error to? Talk with your groups, figure that out. Okay, now come back to me. What am I going to compare that to? I know that my measurement is off 0.3, but if I wanted to find the percent error, what am I going to be comparing this to? Cambria? Yes, this one, because this is the accurate one, right? This is the one that's wrong, so it doesn't make sense to take this and compare it to the one that we know is not accurate. We're taking our mistake and comparing the error amount to the original. So I'm going to create an extra little column here that I am going to call the percent error column, just because I don't have space, so I'm going to squeeze it in there. How far off were we? 0.3. What are we comparing that to? The accurate. In this case, it's the accurate. Before, when we were comparing our percents, we were comparing usually to the original amount. We're comparing to the accurate amount this time. So 0.3 divided by 6.7. Type that into your calculator. We are going to get a percent, or a decimal that we will convert to a percent. And what do you get when you type that into your calculator? Trace, what did you get? Okay, let's I know I was just teasing a student about precision, but now just give me like 3 or 4 decimals instead of 12. Trace 0.04 what? Thank you. Okay. And that's our decimal, right? So let's convert that to a percent. What is that percent going to be? Gonna move it over to the hundredths place, and that would be 4.47%. Repeat that process. Please find the percent error for each of the others. We know what the error is. We know that we are comparing it to the original, not the original, sorry, the accurate amount. Find the percent error for B and C as well, while I take some additional notes up on the screen to find the percent error. Get those calculations done, please. Okay, who has the percent error for B? What is that percent error for B? Joshua. 1.37%, right? Yep, 1.37%. And for part C, 0.3 divided by 7.3, the accurate measurement. What did we get here? Liv? And type it into your calculator so that you can raise your hand. Devin. 4.1%. Is that 2 decimal places of accuracy there? 2.1%. Thank you. Yes, Joshua. $4.11. Ah, the round. Okay. 4.11%, taking rounding into consideration. Thanks for that correction. Why did this happen? Take a look here. Do you see how here we had 0.3 error and here we had 0.3 error? Look at the percents. Why is this 4.47% and this 4.11%? Why, when these were the same over here, the error was the same, why is it that the percents are different? Quick discussion with your groups. I should hear every table talking here. Why did we get different amounts here? Why did we get different amounts here? These were the same. So why did this turn out different? Tanner. Yeah, we're comparing it to the different amounts, right? Here we're comparing it to the accurate measurement of 6.7. Here we're comparing it to the accurate measurement of 7.3. So yes, the error was the same, but this ended up being less of an error because the actual thing ended up being greater. Yes, Carter. Everyone check that work. 0.1 divided by 6.9. And I agree, I got 1.44%. And this is why, folks, 1.45 if we round. This is why, folks, math practice 3, construct your own viable arguments. Should we just be writing down what someone else said that they got? No, we need to be doing this for ourselves. That way you can find those mistakes when they do come up. All right, and we are skipping an activity. The next activity that we should be doing in this lesson is measuring different things in the classroom. That's not going to do any good in a recording, and we're a little bit short on time here in the classroom. So let's skip ahead to the summary. When we are measuring a length using a ruler or measuring tape, we're going to get measurements that are actually different than the actual length. Sometimes it just happens. Maybe we position the ruler incorrectly. Or maybe it's because the ruler is not very precise. There's always going to be at least a small difference between the actual length and what we measure, even if it's a microscopic difference. And so that's why we need to understand this measurement error and why it comes up in our percentage unit. What we saw here in class, we had our centimeter markings and our millimeter markings. The second ruler is marked with those millimeters, so it's easier to get a measurement to the nearest tenth of a degree, or not a degree, nearest tenth of a centimeter. Just because it's already marked, so it's easier to get that much more accurate. So a line that is actually 6.2 centimeters can be measured as 6.2 centimeters instead of 6 centimeters as it was measured with the first ruler, just because it has those extra markings, so we can be that much more precise. And that leads to this word here, measurement error. Measurement error is the, understand this part, the positive difference between the measurement and the actual value. But measurement is usually expressed as a percentage of the actual value. What that means is we find how far off the measurement is, and we call that the error. And then we compare that error to the actual amount. That is what gives us our measurement error as a percent. Notice that it says we always use a positive number to express the error. Oops, that should be highlighting, not crossing out. We always use a positive number to express that measurement error. And when appropriate, use words to describe whether the measurement is greater or less than. Let's put that all to practice in our cool down. Going back to the cool down. Claire estimates that her brother is 4 feet tall. When they get measured at the doctor's office, her brother's height is 4 feet and 2 inches. So, who is going to be the actual height? Is Claire estimating the actual height, or is the doctor measuring the actual height? Which one should be taken as more serious? The doctor. Okay, thank you. At least we agree with that. Okay. The doctor's measurement should be considered the actual height. Explain your reasoning. Well, he actually measured, right? Where she estimated. And I think an actual measurement is always going to be better than an estimate. Actually measured. So what is the error? Express it in inches. Then what is the error expressed as a percentage of the actual height? This is where I pause the video and let students work on this with their groups, and then we'll come back for the answer. Pause the recording as you work on it yourself. Okay. Now we're back. What's the error expressed in inches? How far off is that? Oren. 2 inches. Don't tell me the answer. Tell me, how are we going to find the answer? How do I find the error expressed as a percentage? What do I do? Good. We'll go to Joshua. Okay, let's pause. You're saying, since this is done in inches and this is done in feet and inches, we need to convert this to all inches first, right? That way we're comparing inches to inches instead of inches to feet and inches. So 4 feet is 48 inches plus the extra 2 inches means his actual height is 50 inches. Great, continue. Okay, and 2 divided by 50 is equal to 0.04, which converts to the the percent of 4%. Great job. Your homework, let's practice this with our lesson 13 practice problems. For today, thanks for watching. We'll see you next time.